Hello and everyone. I am Narayana from Mlritm, working as assistant professor in EEE department. In this session, I am going to explain transformers. Okay, in this session, I am going to explain basics of transformers. What is transformer and what is the operation principle of transformer? What are the different types of transformers? And what is how transformer works under load condition and no load condition, and I am going to derive EMF equation of a transformer. These are the topics I am going to cover in this session. First of all, what is the transformer? Why we are using the transformers? Coming to the definition of transformer, transformer is a static device. Transformer is a static device which transfers electrical energy from one circuit to another circuit without change in frequency. Okay, this is the actual definition of transformer. Okay, it is not the energy conversion device. It is a transfers. It transfers energy. Okay, that is the definition of transformers. It transfers energy from one circuit to another circuit without change in frequency. So transformer is basically having two circuits. One is primary side and second one is secondary side. Okay, these two circuits are isolated. There is no electrical contact between these two circuits. However, there is having magnetic coupling between these two circuits. Okay, these two windings are placed on core. Okay, it provides magnetic path which connects both circuits. So basically transformer having two circuits, two electrical circuits, but there is no electrical contact between them, but they are magnetically coupled. Okay, here this is the transformer basic structure or diagram. Okay, it is showing two windings. One is primary winding and another one is secondary winding. So primary winding in the sense the winding which is connected to supply is known as primary winding. Secondary winding means winding which is connected to secondary side, that is load side, that is generally called secondary winding. Okay, these two windings are placed on top of core. Okay, this is the core of the transformer. Okay, this is made of silicon steel. Okay, so these two are isolated. These two circuits are isolated, but there is magnetic coupling between them. Okay, next general question is why we are using the transformers? What is the need of transformers? See, electricity is available at 11 to 25 kV. kV means kilovolts. In power plants or in India, generally electricity is generated at 11 kV or 25 kV. So what we are going to do with this voltage? See, we increase voltage to 132 kV, 220 kV, 400 kV or 765 kV. Okay, so we are increasing the voltage level by using transformers. Okay, what is the advantage of increasing voltage level? See here, by increasing the voltage level of the transformer, what we are doing here, we are reducing the current level. So generally generators generate electricity at power plant. Okay, those electricity or that energy is carried through transmission line and that energy is used by loads which are far away from generators. So generally energy is transmitted through transmission lines. Okay, nearly there may be the distance between generators and load is around 50 to 500 kilometers. So you need to transfer or you need to transmit that energy from generators to load, okay, which are far away from generators. So transmission lines, we know that transmission lines are made of copper. So every transmission line is not a perfect conductor. Okay, it is having losses. Okay, the losses which are present in transmission lines are called copper losses. In other words, I square R losses. So these copper losses are depend on current level. So if current is more, then current copper losses are more. And one more important point is, if current is more, you need to increase the diameter of the conductor. So here what is happening here? So if current level is increasing, that is copper losses increases, and another point is diameter of the conductor increases. That means size of the conductor increases. That means weight of the conductor increases. Weight of the conductor increases means cost of the conductor increases. So what we have to do? Suppose if we reduce the current level, then we can reduce the copper losses in the transformer, copper losses in transmission line. So by reducing, we also reduce the size of the conductor by decreasing the current level. Okay, that is, I mean, this job is done by using transformers. So what we are doing in transformer, we are raising the voltage level near generators. So we are raising the voltage level means we are reducing the current level. Overall power is constant. We know that power is given by V into I, product of voltage into current. So what we are doing here, we are increasing the voltage level. Thereby we are reducing what? Current level. That means overall power remains constant. Okay, we are just raising the voltage level, thereby automatically current value reduces. Why? Because power remains constant. Okay, so by raising the voltage level, we are reducing the current. So that is the overall idea of using transformers. That is the main reason why we are installing transformers in between generators and loads. So in general, generators which are present on power plants is known as power transformers, and transformers which are placed in distribution side or near to load centers are known as distribution transformers. Okay, this is the classification of transformers according to power level. So generators which are placed near power plants are known as power generators, and transformers which are placed near to the load centers or distribution centers are known as distribution transformers. So what we are doing here, see, in India, generally the generator level is 11 to 25 kV. So now what we are doing, we are increasing the voltage level to some voltage, that is 132 kV, 220 kV, 400 kV and 765 kV. In India, 765 kV is the highest level transmission line in India. So step-up transformers are used to send electricity over long distances with less loss. Already I discussed. So by raising the voltage level, we are reducing what? Current. So thereby you are reducing losses. So transformers which raises the voltage level are known as step-up transformer. Transformer which decrease the voltage level are known as step-down transformers. So at what level we are reducing the voltage? See, we reduce the voltage to 33 kV or 11 kV near towns. So generation level is 11 to 25 kV. It is raised to level 132 kV, 220 kV, 400 kV or 765 kV. Again, it is reduced to this voltage level. Again, it is reduced to 33 kV, 11 kV near towns. Further, we reduce this voltage level to 415 volts or 230 volts for homes. Okay, this is the overall idea of transformer, why we are using transformers. So, in order to reduce losses in the transmission lines, and one more point is we are reducing the cost of the transmission line. Okay, this is why we are using transformers. This is the overall view of why we are using transformers. So what is the working principle of transformers? So already it is discussed in first slide. The operating principle of transformer is mutual induction principle. So what is mutual induction principle? See, this transformer is having two windings, primary winding and a secondary winding. I told you there is no direct electrical contact between these two windings. What we are doing here, our source is connected to primary winding. Source is connected to primary winding and secondary winding is connected to load. So we are giving energy to primary winding, but however, here load receives the energy by using this mutual induction principle. So we are getting energy in secondary coil because of energy we are giving to the primary coil. This is said to be induction principle. Okay, right. So what is happening here? How energy is transferring from one circuit to another circuit? That is the question, right? We know this primary winding is connected to source. So what is happening when this primary winding is connected to source? So because now it is having closed path, when primary winding is connected to source, now it is having closed path. Because it is having closed path, some current is flowing through the primary winding. You know, current requires a closed path to flow. So some current is flowing through the primary winding, and we know that current carrying conductor produces flux. Now what will happen? This flux, when source is connected to primary winding, now there is some current through the primary winding. That current carrying conductor produces some flux. Now this flux, this flux travels through this transformer core. Okay, here see dotted lines. I have shown dotted lines on the diagram. This flux travels through the transformer core and it links the secondary winding. So what will happen now? So flux produced by primary winding travels through the transformer core. Now it is linking with secondary windings. So now what will happen when this flux linking with this secondary winding? We know Faraday's law of electromagnetic induction. According to Faraday's law of electromagnetic induction, whenever there is a linkage of flux with the winding or conductor, whenever there is change in flux linking with the conductor, EMF is induced, or in synonym word is voltage. So we are getting some voltage in the secondary coil because of Faraday's law of electromagnetic induction. So here we are getting induced EMF E2 in the secondary winding. However, here in this diagram, the secondary winding is not connected to any load. Primary winding is connected to source alternating supply. Here I am not connecting any load to the secondary winding. However, even though there is no load in the secondary winding, I am getting induced EMF. Induced EMF is there in the secondary winding because of Faraday's law of electromagnetic induction. But there is no current flowing through the secondary winding. Let us suppose I2 is the current flowing in secondary winding. Now I2 is equal to 0. There is no current. Okay. So there is no load connected in the secondary winding. Even though induced EMF is there in the secondary winding, we won't get current because there is no closed path. So definitely when there will be current, when there is load connected to this secondary winding. So whenever there is load in the secondary winding, definitely we have some secondary current, that is I2, which is flowing in the secondary winding of transformer. Okay, this is the overall working principle of transformer. So here what is happening here? So whenever you connect load in the secondary winding, now because it is now having closed path, definitely because of induced EMF some current is flowing, that is I2. So your load receives energy. So what we are doing here, energy which is given to the primary winding, but here we are received that energy in the secondary winding. Okay, that is the working principle of transformer. So I am explaining one more time. So here primary winding is connected to alternating supply. When it is connected to supply, some current is flowing through the primary winding. We know that the current carrying conductor produces flux. Let us suppose pi is the flux. which is produced by primary winding. Now what will happen? This flux travels through the transformer core and it links the secondary winding. So what will happen when it links the secondary winding? Because of Faraday's law of electromagnetic induction, whenever there is change in flux linking with the conductor, EMF is induced. So E2 is the induced EMF in the secondary winding. So whenever a secondary winding is connected to load in the sense it may be resistive load or inductive load or capacitive load, or it may be the combination of RL, RC or RLC, whatever it may be. Whenever there is load in the secondary winding, because of induced EMF, definitely some current is flowing through the secondary winding. So that load receives some energy. Flow of current is nothing but flow of energy. So here load receives energy. Okay. So here energy is given to primary winding, but we are getting energy in the secondary winding. Oh, that is the mutual induction principle. So working principle of transformer is mutual induction principle. So I am going to give some important points regarding transformer. So generally transformer is called constant power device. So what is the point? What is this point telling? Here simply what it is telling, let us suppose this is the core of the transformer. Okay, this is primary winding. Generally primary winding is connected to supply. This is your secondary winding. Secondary winding is connected to load. So constant power device means here, see, power in the primary winding is given by, let us suppose V1 is the supply voltage and let I1 be the current flowing in the primary winding, and V2 is the voltage across load and I2 is the current flowing in secondary winding. So here V1 is the applied voltage, I1 is the current flowing in primary winding, V2 is the voltage across load, I2 is the current flowing in secondary winding. So power in the primary winding is given by V1 I1 cos pi 1. V1 I1 cos pi 1. So pi 1 is the angle between V1 and I1. So this is the power in the primary winding, Vi cos pi. So what is the power in the secondary winding? Power in the secondary winding is given by V2 I2 cos pi 2, or you can say pi 2 is the angle between V2 and I2. In general, transformers, cos pi 1, so cos pi 1 is approximately equal to cos pi 2. So cos pi 1, power factor in primary winding is approximately equal to power factor in the secondary winding. If you consider cos pi 1 is equal to cos pi 2, I can easily write V1 I1 is equal to or approximately equal to V2 I2. Okay, so power in the primary winding is equal to power in the secondary winding. So see, losses are there definitely in transformer. Input power is never equal to output power. Why? Because there are some losses in the transformer. Okay, if we neglect losses or if we treat losses are very small, then I can say definition is, I can say this statement, input power is equal to output power. Losses generally, in the definition, I told you transformer is a static device. Static device means this transformer is not having any rotating parts, no moving parts. In other machines, we have DC machines, induction generators, induction motors, synchronous machines. These are having moving parts, that is rotating parts. So there are losses due to that rotation parts also. That is, your rotor has to rotate against windage, and there is a loss due to friction bearings. There is friction. Okay, so there are some rotational losses present in those machines, but in the transformer, this transformer is not having any moving parts, so there are no rotational losses in transformer. That's why here I can treat, or I can say, losses in transformer are very small. Even I can neglect in some cases if we consider ideal transformer. So input power is equal to output power if we treat losses are small. And one more point is, if we are approximating cos pi 1 is equal to cos pi 2, that is V1 I1 is equal to V2 I. It just transfers energy from one circuit to another circuit. Some losses are there, but they are very small. And one more important point is, transformer is called constant frequency device. See, constant power device means here, see, for the primary winding, we are giving this much of voltage, alternating voltage we are giving, that is V1. So in the secondary winding, that is voltage across the load, the nature of the wave shape is this one. So here V2, let us suppose V1 is having frequency 50 Hz, that is, frequency means number of cycles made per second. So in the secondary side, V2 is also having same frequency, that is 50 Hz frequency. Okay, that is the meaning of constant frequency device. So primary side supply frequency is 50 Hz and secondary side load voltage is 50 Hz. So these are the very important points when regarding to transformer. Transformer is constant power device and transformer is constant frequency device. And one more important point is, it is also called constant flux device. Transformer is also called constant flux device. So what is the meaning of this constant flux device? I told you, so whenever supply is connected to, whenever primary winding is connected to supply, there is current in the primary winding. You will know that current carrying produces flux, right? This flux travels through the transformer core. Let that flux be pi Weber per meter square. So this flux is independent of load. Okay, when secondary winding is not connected to load, or when it is connected to load, this flux always, it is maintained constant in the transformer core. That is the meaning of constant flux device. Okay, I will come to this point later when I am explaining operation of the transformer under load condition. These are the very important points regarding transformer. One is, transformer is called constant power device, second one is constant frequency device, and third one is constant flux device. Irrespective of load, the flux in the transformer is maintained constant. Now, types of the transformers according to voltage level. So there are two types of transformer when corresponding to voltage levels. One is step up transformer and second one is step down transformer. What is step up transformer? Step up transformer means, if we get voltage across the load is greater than supply voltage, then that is called step up transformer. What is step down transformer? If we get voltage across the load which is less than the supply voltage, then that is called as step down transformer. Step up, let us suppose V1 is the supply voltage and V2 is the voltage across load. Let us suppose the secondary is connected to load. V1 is the supply voltage. V2 is the voltage across load. So V2 is greater than V1. Voltage across the load is greater than V1. Then that is step-up transformer. Let us suppose what is step-down transformer. When supply voltage V1 is greater than V2, then that is step-down transformer. In other words, if V2 is less than V1, then that is step-down transformer. What are the construction details of transformer? This is the transformer diagram. It is showing number of parts of the transformers. What the main parts of the transformer are? First one is, this one is core. Okay, this middle core of the transformer, and this is primary winding, and this is secondary winding. Now this is immersed in oil. Okay, generally this transformer is placed in transformer tanks. Okay, here it is. The middle, this one, this is the transformer. Now it is placed in transformer tank. Okay, now in this transformer tank contains some oil. So your transformer or core part of the transformer is immersed in oil for cooling purposes. Here terminal bushings are there. So HT means here high tension, LT means low tension. So high tension means here it is having more number of turns when compared to this winding, that is LT side. So HT side is having more number of turns, LT side is having less number of turns. Okay, and for the transformer production, generally we use Butch Holes relay, and it is conservator tank. Okay, expanded oil or compressed oil is flowing through this conservator tank. Breather is there, silica gel is there, oil gauge is there, some explosion vent is there, radiating tubes are there for cooling purpose. Okay, these are the main parts of the transformer. Now I will come to each point or each part of the transformer and explain how it works and what is the duty of that part. First one is transformer core. Okay, this is the core part of the transformer. This transformer core is made of silicon steel or CRGO steel with lamination 0.3 to 0.5 mm thick. It carries the flux from one circuit to another circuit. It consists of yoke and limb. Okay, this is what transformer core is made of and what is the duty of the transformer core. Transformer core is made of silicon steel or CRGO steel. The duty of transformer core is to carry flux. There are two types of transformers according to core construction. One is core type and second one is shell type. Okay, here diagram is showing core type transformer. Here this is the shell type transformer. What is core type transformer and what is shell type transformer? In core, here the primary difference between them is regarding windings. Here in core type, core is surrounded by windings. Okay, this is core, these are the windings, right? Here in core type transformer, winding core is surrounded by windings. In shell type transformers, windings are surrounded by core. Okay, this is shell type transformer. These are primary and secondary. Windings are surrounded by core. In shell type transformer, here I have shown some differences between the core type and shell type transformer. In core type transformer, there are 2 limbs for single phase transformer. In shell type transformer, 3 limbs for single phase transformer. Here what is limb? Here limbs means here this is 1, 2 and 3. Okay, these are the limbs or legs. Next difference is windings are wound around the two limbs. Here in shell type transformers, windings are wound on the central limb only. Here see the diagram, windings are wound on the central limb. And third difference is flux is same in both limbs. Here see, this core is carrying same amount of flux. In shell type transformer, central limb has flux pi. Okay, this is central limb. Okay, it carries flux pi, while other two limbs have only flux pi by 2. The other two limbs carries only pi by 2 here, but central limb carries flux pi. So in core type transformer, it is having single magnetic circuit. In shell type transformer, it is having double magnetic circuit. In core type transformer, windings surround a considerable part of the core. And shell type transformer, core surrounds a considerable portion of the windings. In core type transformer, cylindrical concentric coils are used. In shell type transformer, sandwiched or multi-layered disc type coils are used. Core type transformer construction is difficult. Shell type transformer construction is easy. Core type transformer is rarely used. Shell type transformer is widely used. These are the main differences between core type and shell type transformer. Next part is windings or coil. So generally windings are made of copper. So winding is classified into two types: concentrated winding and sandwiched winding. See, in general, windings are not separated. See, in previous diagram, I have shown transformer like this. There is primary winding on one side and secondary winding on another side. Okay, it is not like that. In general, windings are placed on top of each other. They are not side by side, on top of each other. The only reason is to reduce leakage flux. Okay, we have very important definition: leakage flux. What is leakage flux? Here, the flux produced by your primary winding will not link the second winding. The entire flux which is produced by primary winding will not link second winding. Some flux leaks through the air. That is said to be leakage flux. Okay, so in general, transformers windings are placed on top of each other in order to reduce the leakage flux. They are placed on top of each other. Next important part is transformer tank. A transformer tank is a sealed container that houses the core windings and insulating oil of the transformer. Transformer tank is sealed container that houses the core windings and insulated oil of transformer. Second point is its primary function include protecting these components from the external environment, providing mechanical support and ensuring proper insulation and cooling. Third point is transformer tanks are typically made from steel or aluminum. The tank is usually cylindrical or rectangular shape, designed to accommodate the core and windings. Tanks are designed to be leak-proof and straight to prevent oil loss and the entry of contaminants. So transformer tank is made of steel. Next one is transformer oil. So what is the duty of the transformer oil? The insulating oil which is used in the tank of the transformer is called transformer oil. What are the functions? It carries away the heat produced in the core and windings. We know that windings carry current. We know windings are having copper losses. So because of those losses, those windings get heated. Okay, now the duty of the oil of the transformer is to absorb the heat produced by your windings. The second one is additional insulation for winding. Next important point is conservator. It maintains oil level in the tank. It provides space for the expansion of oil when the temperature of the transformer is increases. Next one is breather. What is the duty of the breather? The function of the breather is to prevent entry of moisture in the air and allows dry air into the transformer. Next one is moisture reduces the dielectric strength of the oil. Terminal bushings. What is the duty? Terminal bushings provide the necessary insulation to prevent electrical leakage or shorts between energized conductors and the ground root transformer tank, typically made from materials like porcelain, epoxy resin, or high temperature nylon for insulation. And next part is explosion vent. An explosion vent is a safety device on a transformer's tank that protects against internal pressure buildup due to faults such as short circuit. Oil gauge. An oil level gauge is used to visually monitor the oil level within the conservator tank of a transformer. Okay, now I am going to derive EMF equation of a transformer. See, this is the transformer. So primary winding is connected to supply of voltage V1. Now it is going to give some current through the primary winding because of this voltage. Let us suppose that current is Im, or magnetizing component of current. Now this current carrying conductor produces flux which travels through transformer core. According to Faraday's law of electromagnetic induction, there is EMF is induced in the secondary winding because the flux is linking with secondary winding. So E2 is the induced EMF in the secondary winding. Here see, the same flux also linking with primary winding. So there is also some EMF induced in the primary winding. So E1 is the induced EMF in the primary winding. E2 is the EMF induced in the secondary winding. Right. Consider some voltage V1 of frequency F is applied to primary winding. Now this, because this voltage is given to primary winding, some current is flowing in the primary winding. That current produces flux. Let us suppose that flux is pi. So what is the nature of the flux? The nature of the flux is also sinusoidal because supply voltage V1 is sinusoidal. So Faraday's law of electromagnetic induction says whenever there is change in flux linking with the EMF with the conductor, EMF is induced in the conductor. So induced EMF is given by E1 is equal to d psi by dt. Here psi is the flux linkages. Psi is the flux linkage. Let us suppose N1 is the number of turns of the primary. So this Im produces flux. That pi links N1 number of turns. So total flux linkages are given by N1 into pi. N1 into pi. Now that implies E1 is equal to d by dt of N1 into pi. So E1 is equal to N1 into d pi by dt. Okay, that is written here. E1 is equal to N1 into d pi by dt. Here I have placed negative sign. This negative sign is due to Lenz's law. I will come to this Lenz's law later. But induced EMF is given by N1 into d pi by dt. We know that the flux is given by pi m sin omega t. So pi is equal to pi m sin omega t. Now we do derivative of this part, that is derivative of sin is cos omega t, and cos omega t into omega. So equation becomes minus omega into n1 into pi m into cos omega t. So omega is 2 pi f, angular velocity, angular frequency. So 2 pi f n1 into pi m into cos omega t. Now cos omega t can be written as sine of omega t minus 90. So now from this equation, that is 2 pi f n1 pi m sine omega t minus 90. So the maximum value of induced EMF is given by 2 pi f n1 into pi m. Okay, that is the maximum value. EM1 is equal to 2 pi f into n1 into pi m. But we know that relation between RMS value and maximum value. ERMS is equal to EM by root 2. We know this relation. VRMS is equal to VM by root 2. So if you do that, that is induced EMF E1 is given by EM1 by root 2. Here E1 is the RMS value. E1 is the RMS value. EM1 is the maximum value. E1 is the induced EMF, that is RMS value. EM1 is the maximum value. So finally the expression becomes E1 is equal to 4.44 f into n1 into pi m. Okay, this is the induced EMF in the secondary winding. So similarly, if we do derivation for induced EMF in the secondary winding, that is going to be the same. However, the only term that will change here is 4.44 f into n2 into pi m. So here n2 is the extra term in the secondary winding. So E2 is the 4.44 f into n2 into pi m. Okay. E1 is the induced EMF in the primary winding. E2 is the induced EMF in the secondary winding. Okay, this is the induced EMF equation of a single phase transformer. So in this session I have covered what is transformer, why we are using the transformers, and what is the working principle of a transformer, what are the different types of transformer we are using, how transformer transfers energy from one circuit to another, and we derived EMF equation of a single phase transformer. Okay, that is for all for today's session. Thank you.